This video is on section 3.4 notes, graphs of polynomial functions. So first we're going to be looking at what information we need from a polynomial equation so that we can sketch a graph of the polynomial function. And the first thing I like to do is look at the leading coefficient and then also look at the degree of the function. Those are the things that are going to be helpful for us to see the overall shape of the graph. So it says, when sketching a polynomial function, the degree and leading coefficient determine the general shape of the curve as well as its end behavior. And when we talk about end behavior, there's formal ways to write it, which is this. This is notation especially that's used in calculus, kind of introduced in pre-calc and then focused on in calculus. But really what I mean by end behavior is where the arrows go. Do they go left and down, right and up, left and up, right and down? What do the arrows do? That's what I mean when I say end behavior. So when we talk about the degree of the function, we're talking about the highest exponent. So typically when you write a polynomial function, you write each term and you put the exponents in descending order. So typically, if you look at the first term, if the polynomial function has been written in standard form, that first term is going to have the highest exponent, and it's going to tell you the degree of the polynomial. So if the degree is odd, it follows the end behavior from these two pictures. If it's even, it follows the end behavior from these two pictures. And then what determines which picture you choose is whether the coefficient that goes with that term is positive or if it's negative and it has reflected the graph over the x-axis. So if you need something to kind of relate this to, like a context in math that you've already learned, you can think of an odd graph as either like a cubic function or a linear function, even if you want to get more simple. So we have x to the third, which look kind of like this. So we go up, or a linear function would be even more simple, right? It goes up to the right, slants up. And so we know that if the degree is odd and if the coefficient is positive, if it's greater than 0, then this is the way that the arrows go. If we have a negative x to the third or a negative coefficient with an odd leading exponent with an odd degree for the function, then it's going to look like this overall. So these graphs, the reason that these sketches here have only done the ends and have left out the middle is because when you start to add more and more terms, having x to the third in front but then adding x squareds and x's and numbers on the end, what starts to happen is this part in here might have some squiggles in it, but overall the general shape looks like this. So if you kind of like zoomed out from the picture, this is what it would look like, but maybe if you zoom in, you would see some squiggles in the middle. And then we have the even degrees. So if you have a positive coefficient, you're going to end up with something that looks like this. If you have a negative coefficient, you're going to end up with something that looks like this. And then again, we're kind of missing the middle part because if we start to add more and more terms to our polynomial, we might get some squiggliness in the middle, but overall we're going to have this general shape. The other thing that the degree reveals is how many roots a function might have. And another word for roots would be zeros of the graph, places where the function equals 0, or x-intercepts. So roots, zeros, x-intercepts, those are all synonyms of each other, and the degree tells you how many, quote-unquote answers you should have if you were to solve that polynomial. More on that later. Okay, so next we want to look at the behavior at the x-intercepts, because now that we have kind of a big picture perspective, we want to know what's happening in between with the little details if we zoom into the graph. So when you're sketching a polynomial function, the multiplicity of each root determines the way the curve moves around and through the x-axis. So if we have a multiplicity of 1, that means that when we look at the polynomial function, if we looked at it where we could see the roots or the zeros or the x-intercepts clearly, then we would see it in the factored form. That's the easiest way to see a root or a 0 or an x-intercept, if it has a multiplicity of 1, it would be the parenthesis of the root written like this, and it would have no exponent. It would be a factor that only happened one time. And the way that that looks on a graph is it looks like a straight line going through a point. That's what the root looks like. And you can have a straight line that goes through the point with kind of a positive slant, or you can have a straight line that goes through the point with a negative slant. You could have either situation. If we have a root with a multiplicity of 2, or a multiplicity of 4, or 6, or 8, any of the even numbers, then you might have a root that looks like this in its factored form, but it will have an exponent of 2, which shows that that factor happened twice. Or if it's even, it would happen 4 times or 6 times or 8 times, but typically we're going to look at roots that happen just twice. And so the way that looks at the x-intercept is it looks kind of like a mini parabola within the problem. And here it says, if k is the multiplicity, then if k is even, the graph touches but does not cross the x-axis. So some people say this is like it bounces off the x-axis. All right, and then if the multiplicity is 3 or another odd number, 3, 5, 7, something bigger than 1, but still odd, then it kind of does that S curve, or it squiggles as it goes through. So this would mean that when it was in the factored form, that particular factor happened 3 times, or 5 times, or 7 times. And so it squiggles as it goes through. Now here it says if k is odd, then the graph crosses the x-axis, but doesn't say how it crosses. So if it's a multiplicity of 1, it's going to go straight through. If it's a multiplicity of 3 or 5 or 7 or something bigger, then it kind of does that S curve as it goes through, or in my mind I think of it as like it squiggles as it goes through. So to remember the multiplicities, I always think straight through, bounce, squiggle. That's how I remember them, and that's kind of how I'll refer to them to help you guys remember them as well. So it could be helpful to write this straight through, bounce, squiggle through. Okay, so now what we're going to do is, before we do some sketches of our own, I just want to look at some polynomial functions that have been graphed already, and then use what we have learned on the previous page of notes to write their equations. So if we look at this first one, we can see that the arrows go in opposite directions, and that only happens with an odd degree. So we know that this degree is odd. We know that the arrow goes down on the left side and up on the right side, which is a positive slant overall. So we have an odd degree with a positive coefficient. All right, I can see that I have an x-intercept here at -3, which means my parentheses would be x plus 3. This is +1, so my parentheses would be x minus 1. And this is +4, so my parentheses would be x minus 4. And then I just have to look for the multiplicity of each of these roots. And we go straight through right here, straight through right here, straight through right there. All of these are a multiplicity of 1. Now, if it's a multiplicity of 1, you can write the 1, but most people do not write an exponent of 1. They just leave it out. So I would write that this equation is y equals x plus 3, x minus 1, x minus 4. And here, it doesn't matter what order you put these parentheses in, they're being multiplied. I typically do left to right, but it truly doesn't matter. Okay, on this next one, we have 2 arrows pointing down. The 2 arrows are in agreement, both down, both up, if it's got an even degree. So the degree here is going to be even. Since both arrows would be pointing down in this graph, that means we have a negative coefficient. So now I'm going to go through and look at each x-intercept. So this is -2, which means the parentheses are x plus 2, +1, so that's x minus 1, +3, so that's x minus 3. All right, so this one bounces, that's a multiplicity of 2, straight through right here, straight through right here. So y equals negative coefficient, and then I just need to write all my parentheses. X plus 2 squared, x minus 1, x minus 3. Okay, the arrows go opposite directions, and so I know that my degree is odd. If I put my pencil where my arrows are, I can see I have an up arrow first and a down arrow second. That's a negative slant, and so this is going to have a negative coefficient. And then I'm going to look at what my x-intercepts are. So that's at -5. I'll put x plus 5 in parentheses. Then I've got -1, so x plus 1. +4, so x plus 4. Nope, not plus, minus. Then over here I've got 7, so x minus 7. Okay, and then I just need to figure out the multiplicity for each root. So this is a bounce, that's a multiplicity of 2. Straight through right here, that's 1. This is a squiggle through, so that's a 3. And straight through right here, so that's a 1. And if you ever have trouble figuring out the multiplicity when you're kind of standing back looking at the big picture, you can always just say, if I'm looking at the multiplicity of this root, I can cover up everything else and just look at the graph where it goes through that root. And then it's a lot easier to tell, like, oh, that's definitely straight through. Or if I look at the graph just where it's at that x-intercept, oh, that's definitely a bounce. So if you're having a hard time, that's one trick that seems to have worked for students in the past. Okay, negative coefficient, I'm just gonna write all my parentheses. X plus 5 squared, x plus 1, x minus 4 to the third, x minus 7. Okay, both arrows agree, they both go up, and so I know that this degree is even. Since they're up and not down, I know this is a positive coefficient. And then I'll just go through and write down what each of my x-intercepts are. So this one is x, that's 0. You could write x plus 0 or x minus 0 in parentheses, but most people would not. Most people would just write x and stick it in the front of the equation. This is +1, so I'm going to write x minus 1, 2, 3, x minus 3, and x minus 4. And then all of these are straight through, straight through, straight through, straight through. So all of those are 1s. All right, so anytime you have a graph that goes through 0, you're not going to put it in parentheses. Typically, it's not wrong if you do, but typically not. You're just going to put an x there. And no matter where it's written in here, it is common to put that one right in the front, because if you had factored that yourself, you would have taken that x out as a GCF. So it's common to put that in the front. I would have written it that way anyway because I'm writing these left to right, but if the graph had some zeros over here, some x-intercepts over here, I still would have written this one in the front. It is not wrong if you don't. People will just look at you like you're a weirdo. So trying to help you guys out. All right. All those are a multiplicity of 1, so we just write them down, positive coefficient. Okay, I do want to address one thing, this notation here. So when it says the limit as x goes to infinity of f of x equals infinity, this is just a fancy way of writing this picture. It's just writing this picture in math notation. So I'm going to write out the limits that describe the end behavior for each of these problems, just so that you can understand how or why they wrote them that way. So we always do the left arrow and the right arrow. We always describe both. So we're going to say the limit as x goes to negative infinity. That's me describing the left arrow. The limit as x goes to positive infinity. That's me describing the right arrow. And then when you describe each arrow, you're going to say whether they go up or down. So the left arrow of the function goes down, so that's negative infinity. I wrote these really close together. And then the right arrow of the function, it goes up, so that's positive infinity. Okay, so we'll do it again. Limit as x goes to negative infinity. Limit as x goes to positive infinity. So this is me looking at the left arrow. So look at the left arrow of the function, and I can see that the left arrow of the function goes down, so that's negative infinity. Now I'm looking at the right arrow of the function. I can see that also goes down, so that's negative infinity again. All right, the limit as x goes to negative infinity, I'm looking at the left arrow. For this one, the left arrow goes up, so that would be positive infinity. Now I'm going to look at the right arrow as x goes to positive infinity. That's the right arrow. And the right arrow goes down, so negative infinity. All right, last one. I'm going to look at the left arrow. So limit as x goes to negative infinity of the function, telling me to look at the left arrow. The left arrow goes up. This one's telling me to look at the right arrow. The right arrow also goes up. All right. So next we're going to graph a couple of these on our own. So to find the degree of the function, you have to add the multiplicities together. You have to imagine what would happen if you multiplied all these parentheses out. If I wrote x minus 3 twice, x plus 5 3 times, and like FOILed the whole thing, multiplied the whole thing. So the degree equals the multiplicities added together. So sometimes the degree is easy. Like in this example, the degree is easy. It's just 3 because this one's written out already. But the ones that are in factored form, you just have to add the multiplicities. So for this one, we have a multiplicity of 3 and 2. This multiplicity is not written, so that means it's a 1. That's the only exponent you don't write. So the multiplicity of this equation is, well, not the multiplicity, the degree of this equation is 6. There's no number in the front, which means that it's not negative, so it's a positive coefficient. So when we have even degrees, you either have both arrows going up or both arrows going down. This is a positive coefficient, so we're going to have both arrows going up. We have 3 x-intercepts. We have x equals 0, x equals 3, x equals negative 5. 0 has a multiplicity of 1, 3 has a multiplicity of 2, negative 5 has a multiplicity of 3. All right, so we have an x-intercept at -5, 0, and 3. Okay, so for 5, -5, it's a multiplicity of 3. So I have to draw a multiplicity of 3 so that it connects to this arrow, and so it kind of makes sense in the graph. So there's two different ways to draw a multiplicity of 3. You can go down, level off, go down. That's one way. The other way is to go up, level off, and go up. And if you think about connecting to this arrow, going up, leveling off, and going up doesn't make sense because your arrow would be down here. So the first option, this one, is the one that makes the most sense. So that's the one I'm going to draw. Okay. So I'm starting with an up arrow. Next, through 0, I have a multiplicity of 1. These are the easiest to draw. You're just going to go straight through. But if we wanted to be technical about it, you can go straight through with kind of a positive slant, or you can go straight through with a negative slant. So with this one, you can tell that if I have to connect this to this, I'm going to have to go for the version that has a positive slant. That's the only way for me to connect those two graphs. And we always make sure with polynomial functions that we connect them with smooth curves, because polynomials are very nice, smooth curved graphs. All right, and then the positive 3 has a multiplicity of 2, and so you have two options for that. It can be a U-shape that bounces above the graph, or a U-shape that bounces below the graph. And if we have to connect to this and we have to end with an up arrow, it only makes sense to use the bounce above the curve, or above the x-axis, I mean. So I'm going to do this one, and then I'm just going to connect those two with a nice curved line. All right, and you'll notice that I drew my little lines across the x-axis by 1 so that you could see what my numbers are there. But on the y-axis, I didn't label anything because I don't know what those numbers are. So I don't know how far down this goes. I don't know how far up that goes. So since I didn't label the y-axis, it makes it so my graph is a reasonable sketch to be accurate, but it doesn't matter because there's no numbers here. For the next polynomial, we have -x² times x plus 5. So again, I need to find the degree, and I can do that by just adding the multiplicities together. 2 plus 1 is 3. And this time we can see that the coefficient is negative. I have two x-intercepts, 0 and -5. 0 has a multiplicity of 2. -5 has a multiplicity of 1. So when I have an odd degree, I know that the arrows go opposite directions. And because the coefficient is negative, I know that I'm going to have a negative slant to my graph overall. And so my first arrow should go up and my second arrow should go down. Or I should say my beginning arrow and my end arrow. Okay, so 3, 4, 5. There's 0 and -5. 1, 2, 3, 4, 5. Okay, so through -5, I have a multiplicity of 1. You can just start drawing at the arrow and just kind of go straight down if you want, but I always think of it two ways. We can have kind of a positive slant, or we can have kind of a negative slant, and then I think which one would make the most sense with this arrow. And this positive slant would not make sense because the arrow would be kind of cutting across the graph. And so I have to go with the negative slant for this graph to make the most sense. And then for 0, I have a multiplicity of 2, so it's going to bounce. So I can have bouncing from above or from below. And to be able to connect to this part of the graph and then also connect to this arrow, it only makes sense to go from below. So there's my arrow going down, and then I have to connect these two with a smooth curve. And so there is my polynomial function. All right, this last one, I can see the degree is 5. There's nothing written in the front, so that means it's got a positive coefficient. We have x-intercepts at -3 and positive 1/2. So anytime you have a number in front of the x, it means that this is going to be a fraction. So positive 1 divided by 2, positive 1/2. Multiplicity of 3, multiplicity of 2. So odd number degree means that the arrows are going to go opposite directions. And then a positive coefficient means we're going to have a positive slant or a positive slope there. So the starting arrow will go down, the ending arrow will go up. So there's -3, there's positive 1/2. And so through -3, we have that multiplicity of 3. So we're going to go up and kind of level out and go up. That's one option to connect to the arrow. The other option is to go down, level out, and go down. And this version going down would not connect to the arrow very well. It would have to kind of go backwards. And so I'm going to do the first option here. So there's my arrow, and then I have a multiplicity of 2, so I've got two options. It can be above or below, and to connect to this and connect to the arrow, it makes more sense for it to be above. So that's how I'm going to draw it. There's the arrow, and then I'll connect these with a smooth curve. And there's my polynomial. All right. Now, this next one is a little bit different because we have a polynomial that's in standard form. And so you can't readily see what the x-intercepts or the roots are. And so to get this one ready to graph, we have to find the x-intercepts, we have to find the roots, which means we have to factor it. So we have to go back to where we know how to factor something that is written like this. And you have two methods that you've learned in the past. One is to take something that has 4 terms like this and split it in half and try to factor by grouping. If I can factor the first 2 terms, take a GCF out, factor the second 2 terms, take a GCF out, and then if both of the remaining sets of parentheses are the same, then I can factor by grouping. And unfortunately, this problem does not factor by grouping, and so we have to do the new method that we learned in this chapter, which is to use the rational root theorem and factor it that way. So I'm going to list all the p-values, the factors of the constant, 1 and 3. All the q values, the factors of the leading coefficient, so just 1. My possible roots, 1 divided by 1, so plus or minus 1. 3 divided by 1, plus or minus 3. So thankfully this one doesn't have too many possible answers. So I'm going to try positive 1 first, store that for x. X to the third minus 5x to the second plus 7x minus 3. And I will know that that is a root if this evaluates to be 0. Ooh, and it does. That was lucky. Okay. So now I'm going to do synthetic division to find out what the remaining polynomial is that I can then factor if I take out the first root. So I've got 1, -5, 7, -3. And I could do polynomial long division, but I'm doing synthetic division because it's faster. So 1 times 1 is 1. Add those together. -4 times 1 is -4. Add those together. 3 times 1 is 3. Add those together. And I get a remainder of 0 because it was a factor. All right, so if this is x to the third, that means this is x squared. So I've got x squared and x. So when I take out one of my factors, this factor was a factor of x minus 1, and that's how you get the root of positive 1. Then I just need to factor this remaining quadratic, and then I'll know all the factors for this polynomial. So I'm looking for, let me write this out there. I'm looking for two numbers that multiply to be 3 and add to be -4. And the two numbers that would do that are -3 and -1. So this is x minus 3, x minus 1, which means that in factored form, I have f of x is x minus 1, that's from the original root that we found, and then x minus 3, x minus 1 from the factoring that I just did, which means I can write this as x minus 1 squared times x minus 3. All right, so I can tell this is an odd degree because it's 3, has a positive coefficient, so I know that the end behavior or the arrows are going to be that it goes down first and then up. I know that I have an x-intercept of 1 with a multiplicity of 2 and an x-intercept of 3 with a multiplicity of 1. Okay, so 1 is going to be a multiplicity of 2, so it can either look like this or like this, but it has to have a down arrow first. So I'm going to draw it like that. Kind of made that look bad. Oh well. Okay, and then through 3 I have a multiplicity of 1, so I can kind of have a positive slant there or have a negative slant. And to connect from here to here would be very weird. So I'm going to do a positive slant and go up and then make sure that these are curved when they connect together. There's my polynomial for that one. All right. So next we're going to solve polynomial inequalities, and we'll do that by graphing, but we're also going to do it using test points, which I'm going to start calling sign charts, just because that's what a lot of other people in math call them. I'll probably still refer to them as test points actually, because I think that's what my math lab does and I don't want to confuse you guys. Okay, so I'm going to sketch a graph of this to help me solve the inequality. So that's a multiplicity of 1, so this is a degree of 3 with a positive coefficient. So I know the arrows go like that. I have an x-intercept of -2 and an x-intercept of 4. -2 has a multiplicity of 2. 4 has a multiplicity of 1. So there's -2, there's 4. So for multiplicity of 2, I have these two options. So I'm going to start like this. And then positive 4, I have multiplicity of 1, so I can do a positive slant or a negative slant. So this one, positive slant, makes more sense. And then we'll just connect these, the smooth curve. Okay, so there's my sketch. And the problem says that the answers are those that are less than or equal to 0. So the problems that are equal to 0 are those that are on the line. Those that are less than 0 are those that are below the x-axis, because we're thinking about the outputs. The outputs of the function would be the y-coordinates. So y-coordinates are going to be negative down here, and they're going to be positive up here. So that means that all of these values work, and so our solution is going to be -infinity to 4 inclusive, which means we include the 4. All right, if we were to do this with a sign chart or by using test points, then I would put -2 and 4, and I would not ignore this because once we get to more complicated problems, you're not going to want to graph everything. So the graphing is a little bit easier in the simple problems, but there's a point where you're going to use a sign chart for everything. And especially if you decide to go on to calculus and take that course, sign charts are exclusively what you're going to use by the time you get there. So it says less than or equal to 0. Since it says equal to 0, I'm going to include the -2 and include the 4 because those values are where we equal 0. So I'm going to choose numbers to test. A number less than -2 would be like -3. 0 is in between. 5 is above. So I'm just going to test each of those values. And then I love when a problem is written in this factored form because it makes it super easy to plug numbers in and see if they work. So for this first set of parentheses, a number plus 2 squared, it does not matter what I plug in for that number. This is always going to be positive because I'm always squaring it. So I'm going to say that for this one, I'm going to get some positive number multiplied by x minus 4. And you'll follow what I'm doing in a second. So this is always going to be a positive number. Okay, -3 minus 4 is a negative number. So for my first sign that I'm trying to see with my sign chart, or with my first test point that I'm doing, I have a positive number times a negative number. And positive times negative is negative. All right, then if I plug in 0, 0 minus 4 is negative. So I have a positive number times a negative number. Positive times negative is negative. Then for the last one, 5. 5 minus 4 is 1. That's a positive number. So I have positive times positive. That's a positive number. So then I can look and say, all right, what part of it am I supposed to be using for my answer? Well, this is less than or equal to 0. That means that the negative signs are my solution. And so the negative signs are this whole part that is to the left of 4, or negative infinity to 4. So that's how you could do this problem using just a sign chart. Okay, and then one last example. So we have a problem, again, it's not in the factored form, and so we need to find the factors so that we can know what the roots are, so that we can go through and graph this, or so that we can go through and make our sign chart. So the p-values, there's a lot more of them this time. 1, 2, 3, 4, 6, 9, 12, 18, goodness gracious. Okay, 36 has a lot of factors. I think that's all of them. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. Okay, so that's all of those, and then Q is just 1, thank goodness. So the possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 36. Okay, hopefully one of the small numbers works. So I'm just going to start plugging these possible roots in and see which one gives me 0, because then I'll know it's a factor. Not 1. Oops. Not -1. Okay, it's 3. All right, so 1 times 3 is 3, that adds to 4. 4 times 3 is 12, that adds to negative 3. Negative 3 times 3 is negative 9, that adds to negative 12. Negative 12 times 3 adds to multiplies to negative 36, and then those add to 0. So that's exactly what I wanted. Since this is an x to the 4th, that means this is an x to the 3rd, x squared, x, and no x. We have not seen a problem like this yet, where we found one of the factors. This factor was x minus 3, and it's still not ready to factor. So if we look at this problem, or maybe it is ready to factor. So we've got two ways that we could do this problem. Remember, when it's got 4 terms like this, we can do factor by grouping. So I can split this in half, and I can factor the first 2 terms by taking out the GCF. I have a GCF of x squared. That leaves x plus 4 behind. Over here I have a GCF of negative 3. That leaves an x plus 4 behind. This is really great. So this is one method. You can factor by grouping. The other method, if you could not factor by grouping, is that you could do the rational root theorem again. You could look at the p's for 12, look at the q's for 1, go through this process again. The really nice part here is that this one is actually able to be factored by grouping, so that's perfect. So we have a GCF of x plus 4 and leftovers of x squared minus 3. All right, so in the factored form, we have the function is x minus 3, x plus 4, and x squared minus 3. This is difference of squares. Even though 3 isn't a perfect square, you can still think of it that way. So if you wanted all of the roots kind of broken down all the way, that last one would be x plus root 3 and x minus root 3. So you could do the graph like this. And this time I'm going to go ahead and do the sign chart first, and then I'll show the graphical way to make sure that our answer is right. So we have 4 roots. We have x equals 3, negative 4, negative root 3, positive root 3. And I just want to make sure I know what the square root of 3 is. It's 1.7. So I'm just going to keep in mind that these are 1.7 for when I draw my sign chart. So negative 4, negative 1.7, 1.73. Okay, so it says less than 0. These are all where the graph equals 0. So since we want the values that are less than 0, I can't actually use any of these values. So I'm putting an open circle on all of them, and then I'm going to choose values to plug in. So I've got negative 5 to plug in, maybe like negative 2 right here, 0, positive 2, 4. Okay, and then I'm going to write down the parentheses that I'm using. So x minus 3, x plus 4, x plus, I'm going to use the 1.7s because they're easier for my brain. When I finally write my answer, I am going to write it with the root 3s though. Okay, so for the first one, negative 5 minus 3 is a negative. Negative 5 plus 4 is a negative. Negative 5 plus 1.7 is a negative. Negative 5 minus 1.7 is a negative. 4 negatives multiplied together are positive. Okay, let's try it again with negative 2. Negative 2 minus 3 is a negative. Negative 2 plus 4 is a positive. Negative 2 plus 1.7 is a negative. Negative 2 minus 1.7 is negative. Okay, so this is 3 negatives, so that's going to be a negative answer. All right, let's do 0. 0 minus 3 is negative. 0 plus 4 is positive. 0 plus 1.7 is positive. 0 minus 1.7 is negative. So this is a negative, nope, this is a positive answer. Okay. 2. 2 minus 3 is negative. 2 plus 4 is positive. 2 plus 1.7 is positive. 2 minus 1.7 is positive. So there's a negative. I'm sensing a pattern here. And then last one, 4 minus 3 is positive. 4 plus 4 is positive. 4 plus 1.7 is positive. 4 minus 1.7 is positive. Okay, so if we want the answers that are less than 0, that are negative, then we've got 2 intervals here and here. So my first interval is -4 to -1.7. -4 to -√3. And then my second interval is 1.7 to 3. √3 to 3. There's my answer. So that's how you can do it without a picture. If you want to do it with the graph, we know that this degree is 4. We have a positive coefficient. There's no negative in the front, so this is a positive coefficient. We have the x-intercepts of 3, -4, -√3, positive √3. So both of our arrows are going to be in agreement. They either both go up or both go down. So here they're both going to go up. Then we've got 1, 2, 3, 4, -4, 1, 2, 3, 4, positive 3, -1.7, positive 1.7. And then all of these parentheses are a multiplicity of 1. And these graphs are very easy to draw because you just go straight through, straight through, straight through, straight through. So we're going to start from up, and we're going to go straight through, and then straight through, and then straight through, straight through. There we go. So we know that we could not equal 0 for any of these, and so I'm not going to fill in my circles. And it said that we had to be less than 0, so underneath. And so you can see -4 to -√3, positive √3 to 3. So you can do it graphically, you can do it with the sign chart, but just make sure you don't completely ignore the sign charts because we will be exclusively using those at some point. They're a great method for solving inequalities.